I'm Jun SHIMADA from JAXA. In this session, we're going to talk about space resource utilization. It's about creating fundamental products such as oxygen, water, propellant, and construction materials from local leases on space destinations. To make that happen, technologies on the ground could be applied in many ways, which is the reason we created this session to discuss the intersection between terrestrial mining and space resource utilization. And this event is sponsored by CSIRO, ESLIC, and JAXA. I'd like to say thank you to their sponsorship. With that sort of brief background, I'd like to introduce the speakers. Well, from left to right, Marianne Cummings at Strategic Development at AEST Mine, and Professor Angel Abud Madrid from Colorado School of Mines, and Andrew Dempster from Australian Center for Space Engineering Research at UNSW, and Mark Saunter from Off-Earth Mining, Chairman of Off-Earth Resources, and Catherine Hadler, Director of ESLIC, European Space Resource Innovation Center, and Jonathan Ralston, Senior Principal Research Scientist from CSIRO Mineral Resources, right? And myself, I'm a technical lead for ISL research at JAXA. JAXA Space Exploration Center. It's so fantastic. It's so fantastic to have you all here in the panel. Thanks for making this happen. All right, let me start. Yay. Well, let me start with you, Jonathan. For those who are not familiar with space resources, what exactly the ISRU is?
This one on. Thank you, Jun, and hello, everybody. ISRU, you're talking about a topic that we all love here, so I'm very happy to talk about that. Before I get into space resources, it's probably very helpful just first to think about our conventional terrestrial resources, where we all understand Australia has abundant and rich resources, and it's our capacity to utilise and access those in safe and efficient ways that's really important. We need them for life. We need them for a prosperous society. So that's the terrestrial side, but what about the planetary side? Well, up here on the screen, hopefully, is a picture of the moon. This is some USGS data. And on the left-hand side there, you can see our conventional picture of the moon. But the right-hand side has a false colour map of all different types of rich geological features. And so when we think about resources, there are resources on Moon, Mars, asteroids, and other planets as well. And again, it's our capacity to understand what those resources are and access them in useful ways to support missions and other activities. If I could have next slide, please. So when it comes to in-situ resource utilisation, in-situ really just means where you find it. That's where you can utilise it in the operating environment. It's really about how do we characterise those resources, how do we then intelligently process them and provide the kind of products and services that we need to support mission activity. And so that's a picture of the future on Mars, perhaps, about in-situ resource utilisation equipment. After identifying the resource, we're then able to utilise it, store it, and use it in interesting ways. Next slide, please. For those who like a little bit more detail, this is probably a little bit more of a realistic picture of what an in-situ resource utilisation system looks like. It is actually, in its core, a regenerative system, so it is a closed-loop concept. On the top left there, you'll see the very number one, which is resource characterisation. So a key part to all downstream resources for in-situ resource utilisation is first understanding what resources we have there. Then we need to access it, extract it, transport it, beneficiate it, and after that point, it can go in lots of different directions. You can be using it for construction, you can be using it for chemical reactions to extract elemental volatiles, for production of propellants, life support, and other materials as well. And down the bottom right there, that's where we want to go, that this technology gets sufficiently mature that we can then begin to produce things on the surface to then be reused for other applications. The exciting thing about this panel here today is there are lots of blank boxes there. It's a mixed technology environment. So there's lots of challenges, but also lots of opportunities for us to explore about how we might be developing and building this system, which I also think will be very interesting. We're talking about terrestrial to space, but it's also space back to terrestrial. So thanks, Jun. That's my 3-minute introduction to in-situ resource utilisation. Over to you to rock and roll.
Thanks for your nice introduction, Jonathan. We need great band members to rock and roll.
Looking for band members, come see us afterwards.
Well, let's move on to the short presentation by the speakers. Multidisciplinary collaboration is the key towards sustainable learner activity on space frontiers. And AustMine is the leading industry association for the Australian mining equipment, technology, and services sector. And Malian, please tell us the mission of your institution.
Thanks, Jun, and hi everyone. It's great to be here. As Jun said, AustMine is the peak body for the Australian mining equipment, technology and services sector. We call it METS. You may not have heard of the word METS, but basically what METS companies do is they develop and commercialise technologies and high-value services that are used to solve all the issues in mining. So different to the actual miners themselves. AustMine members range from startups to multinationals to corporates to research institutions and universities. We have over 800 corporate members, and that makes us actually the largest mining innovation hub in the world. And what our members have in common is innovation. Innovation's their lifeblood, and also obviously their deep domain knowledge of terrestrial mining. As we know, there's a lot of, and we've heard already, a lot of overlaps between technologies in space, a lot of the same challenges, difficult environments, but also opportunities. And we were recently asked by the Australian Space Agency to complete a report on the overlap of the technologies between mining, space and METS. And some of the things that we found were really interesting. We found that a lot of, and I think John already mentioned this, a lot of technologies initially invented for space missions are actually being used in mining to make it safer, make it more productive, make it more sustainable. Not everyone realises that in mining itself, but that is actually the case. And conversely, there's actually a lot of technologies developed on Earth for mining that have real application in space. So what we've also seen is technologies maybe initially coming from space being used in mining, then being developed further, then being fed back into space. We call that spin in, spin out, or spin back. And that's a really good thing because that creates a circularity of knowledge that's really important for us to move forward as really, whether it's two sectors or whether it ends up being one. We also found a lot of cross-collaboration opportunities where, each sector could have a particular challenge that can be solved by the technologies of the other sector, or particularly in partnership sort of scenarios. So you can see them there, particularly exploration mapping technologies. These go both ways, by the way, so we're talking about collaboration rather than one having only going one way. Autonomous and remote operations, most mines, or a lot of mines, are remote. Data analysis, simulation, resource extraction, processing, robotics and AI. Energy solutions, advanced materials and manufacturing, environmental monitoring, sustainability, infrastructure and development. Also, we have learned a bit in mining that should be transferable in terms of those environmental factors as well to space. When we did the report, as well as opportunities, we found a lot of challenges. Because you're asking, if there's all these great opportunities, why aren't we seeing more of it? Well, these are some of the challenges that we noted in our report. One of them is a lack of common knowledge. We found lots of instances where mining and space would be essentially talking about the same thing, but with completely different languages and also different perspectives, how they look at the technology, which leads to miscommunication and a lack of understanding. lack of awareness of potential applications. That goes both ways. Stakeholder coordination. There's many associations that are looking at this overlap, but there's not really a coordinated approach. So one of our recommendations in the report was to establish a METS and space cluster, which we have done in association with AROSE, which is the Australian Remote Operations for Space and Earth Association. So we have 120 members and we've had 3 meetings so far. Sorry, my timing keeps changing in front of me. Other things in terms of recommendations, as well as the stakeholder coordination, we looked at skills and how we can, we obviously need more STEM skills, and we looked at education and recommended interdisciplinary courses with space science and mining engineering, so that we can develop a cohort of people who can operate in either industry. And some of my colleagues will talk to that point.
Well, thanks, Marianne. Great insights from industrial perspective. Next speaker is Angel. Let's dive into the first question for you. Given the last comments, Marianne's last comments regarding STEM education, how do you see the role of research and academic institutions to bring together terrestrial mining and the space resource utilization?
Thank you, Jun, and thank you, Marianne, for pointing on your last slide 4 different challenges, which are exactly the areas in which universities excel. To provide the common language that is required on this field, to provide the awareness of the opportunities and challenges, and to generate the workforce that will be needed on this field of space resources. So let me point out some of the areas in which universities can provide expertise. First of all is the basic research, the basic knowledge that is required for all the areas that Jun and Marianne pointed to. We need information on how to identify, how to collect, how to extract resources, how to utilize them, and all the infrastructure that will be needed: power, communications, transport. Very simple examples. The geological knowledge that is needed in order to understand why the resources are where they are in different destinations. What are the mechanical, the chemical, the geotechnical properties of the lunar regolith, which is the main source of these resources. So these are the things in which the university can provide information and start crossing that bridge between terrestrial and space mining. Then we move to technology. This is another area in which universities are really good at, to provide those prototypes, those very early technology demonstrations, testing on analog sites that can be utilized, and even participate on missions to the moon in the early phases, collaborating with organizations such as CSIRO and such as ESRIC, and find a way to explain those things. Right there you can see, for example, a facility that is used for this is a lunar test bed at the Colorado School of Mines, in which companies can and space agencies can come in and test their equipment. There's also vacuum chambers. And these type of facilities are all around the world now. You can find them. I mean, if I just look around here in the panel, in the room, we have facilities at ESRIC, for example, collaborating with University of Luxembourg. We have the University of New South Wales that has these type of facilities, plus mining facilities that can actually work together on this. My colleague in the room, Dan Britt, has at University of Central Florida, a place where you can find the simulants that you need for those type of things, some of the best ones, and also the facilities where you can have competitions with students. And just 2 days ago, the University of Tokyo announced the formation of its Center for Space Resources and Innovation. So you can see that it's not just the excitement about this, but there's all sorts of places where you can conduct these early prototype demonstrations. And then we go to the core of universities, the education, how to provide that information and that transfer of knowledge for young students, for mid-career professionals, and for also people that want to change fields on this area of space resources. At the Colorado School of Mines 8 years ago, we took a decision to say it's time for space resources to become its own academic discipline, not just a side thing for others, but to really take a look at its multidisciplinary aspects. So how to educate scientists and engineers, how to educate entrepreneurs and policy analysts and economists on this field that is exactly the reflection that we have on Earth, but that you will have in space. And now you can see opportunities for education in all of the universities that I mentioned at the beginning. And finally, outreach. Universities are the ideal place to bring together, without any fear, space agencies, commercial companies, lawyers, economists, to discuss things related to space resources. And so you have places like the Space Resources Roundtable at School of Mines, you have the Space Resources Week in Luxembourg, the Off-Earth Mining Forum here at University of New South Wales, in which everybody can come in and exchange areas, exchange knowledge and ideas, so that you can address those challenges that Marianne was talking about. How do you communicate or create a common language between the mining industry, terrestrial and space? How do you make them aware of the opportunities, and how you can develop that much needed skilled workforce for the field of space resources?
Thank you, Angel. The next speaker is Andrew, and one of the key elements is project development. And Andrew, what is the main difference from project development perspective? What is the main difference between terrestrial mining and space resource utilization?
Well, there are a number of differences. Can I have, hold on, let me just get... So the reason why we're able to answer the question that Jun has asked there is that we have always taken the approach of this whole space resources research problem. We've approached it from the mining engineering side. So I'm an electrical engineer, but my colleague Serkan Saydam at UNSW is a mining engineer. And so we look at the mining engineering discipline, how it affects this problem. And that was reinforced to us when we were at Space Resources Week in Luxembourg some years ago. Some guys from Rio Tinto were there, and they were there for the whole week. And at the end of the week, they said, we have learned nothing that we can take back to our board. To come back to communication yet again, the space people, that's probably most of you, are not talking the language that the miners need to hear in order for you to advance a project with them. So in red there, we're saying, well, what we're trying to do is reduce the risk perceived by a potential investor in the space resources venture. Now, that means you've got to reduce all the risks. And there's so much uncertainty here when you compare terrestrial and space mining. The legal framework is not there. The social license is not there. The environmental effects have not been fully affected, and so on. In addition to all the technology and stuff that Marianne was talking about, there are these other issues that we need to address. Now, I'm an old professor. Yes, everyone's very surprised. Now, I don't do much research myself. I watch other people do interesting things, but the one thing that I do myself is to work on this particular problem, the interface between these two industries. Now, you are probably, I'm guessing, mostly space people. Probably quite familiar with the diagram that I put up here from the NASA System Engineering Handbook, where you progress through a project, you go through PDR, CDR, there are reviews, and each of those reviews leads to a go, no-go decision that is primarily technical. If you're a miner, it's a completely different process. There's this feasibility study process that you go through, and you in the diagram on the left, you're going from the top downwards. You're spending some money to find out some information about whether the project should progress, and you make a decision. Then you spend some more money to make yourself more certain, and you spend some more money, make yourself more certain. All of those decisions are based on NPV. They're business decisions. So one of my conclusions is that most of us, including myself, are used to designing products. Most engineers design products. Mining engineers design businesses. It's a different way of thinking, and both the space people, but particularly the space people, have to change the way they think if we're going to be serious about how we go about doing this. So, oh, there we go. Designing a product, designing a business. So there are differences between the two disciplines. I believe most of the change has to happen with the way the space people think. Some of the thinking has to change on the mining side. Now, so the miners tend to be quite conservative. Space is a little bit difficult for them to come to grips with. And I think there's a lot more to it than just talking about the technologies that can be transferred between the disciplines. It's about how you have to start further back, how you actually run through the whole life cycle of the two businesses. And I've come in under time. Just saying.
Thank you, Andrew. Well, given the insights we've got so far, I'd like to dive into the first round of discussion. And I like the first thing I would like to discuss is scalability. I do recognize that there are skeptics who are saying, oh, this is great for research purposes, but it's just unrealistic to develop a large-scale plant on the moon or Mars to produce tons of oxygen or propellant. Considering the transportation mass or periodic maintenance and on-site construction and so on. What's your response to that? Are you asking me? Yeah, or anybody.
So scalability. Now, I think that is an issue that the space community would be quite familiar with, right? You try and do the easy things first and gradually build. Again, it's a different approach. I did an interview with the television yesterday, and I was supposed to do it with Serkan. He has a time frame where he talks about. I don't know if you're going to ask this question later, and I'm going off script. But anyway, he says, okay, in this decade we're doing technology demonstration. Next decade, so 30 to 40, we're doing proof of concept. 40 to 50. Small-scale operations, and only by 50 would you have a mature mine. I know there's probably a couple of people in the audience who want to get arguing about that straight away, but there's scalability in terms of what you're trying to do. But one problem with the idea of starting small is that even starting small still costs you a lot of money. They're saying the first trillionaire will be a space miner. You're going to have a few billions even to get into the business in the first place.
Any comments from the panel?
Is this thing on? Yes. Even in terrestrial mining, however, you can have mines that are very small or very large. So the modern or the prevalent conception of mines as necessarily being huge operations with billion-dollar, multi-billion-dollar capex is not always the case. And in starting up new mines, the aim is generally to try and start up the smallest possible capex and then grow organically. So scalability, I think, isn't as big a problem as people think it is.
Can I just jump in? It's not a big problem as such, but it is one of the problems, it is one of the challenges that we have in not speaking the same language. So to go back to Marianne's point about speaking the same language, as someone who was as a mineral processor, not a mining engineer, but mineral processing, often on a plant we're dealing with 6,000 tonnes an hour through a processing plant. And then when we talk about space resources and ISRU, we're talking about kilos, grams. I mean, these are tiny amounts. The mining industry laugh you out of the room if you talk about these amounts. So it's one of the areas that actually we need to resolve in finding a common language is the issue around scale.
I see it. Angel?
Yeah, and I think to that criticism that we're just starting from basic research, that's exactly where we are in space mining. There are three things that are needed for any extractive industry. You need to know that your resource with enough certainty that it's a proven reserve. You need to know the technology that is needed, and you have to have a customer. And in space resources, we are at our infancy. So we need to start crawling first, try to first find out what resources out there, start developing the technologies, and identify who's interested, who's going to be the customers. So it's going to take a while, but eventually, like in any activity, we'll go from crawling to walking to running.
Right.
That point about the customer, though, is an important one because at the moment there's neither there's neither buyer or seller, and I think there was a contract signed for Helium-3 earlier in the year, but in general, there isn't, no one wants to jump in and commit to needing water in space or something until they know there's a supply, and no one wants to supply it until they know that there's going to be a customer. So it's a bit of a hurdle. That's a genuine hurdle that we need to overcome before we can actually start doing this on a scale.
Okay, yeah, thanks for your insights. Well, in terms of technical challenge, it takes time to reach the point where we can get profits from space resource utilization. And I think it's fair to say space resource utilization is not profitable in the short-term period. So my question for Marianne is, what are the challenges to promote private investment in space resources utilization? I mean, what drives terrestrial mining industry to invest their resource into space resource utilization?
Thanks, thanks, Jun. And I think some of the other panelists have covered the points, but I'd just like to make the distinction here between mining, as in mining houses, mining companies, and the technology companies, the METS companies. So miners operate a mine over decades, and they go through the stages of mining. They find the resource, they construct the mine, they extract, they process, etc., and then they close and rehabilitate. And throughout that whole process, they have to be commercially viable and answerable to their shareholders. So at the moment, there's not really a commercially viable model, which is what all the panellists have said. So I think until there is, it's very unlikely to see at this point that miners will invest in space, because it has to stack up against other potential investments on Earth. And at the moment, it's hard to see how that could happen. And from the METS, the tech companies, they're often SMEs. They may have limited resources. They definitely have to make a profit. And sometimes, well, not sometimes, what we're seeing is, to them, space is esoteric. It's so far away that they can't see any commercial pathway yet. So again, it's a little bit about lack of knowledge.
Yeah, understood. Any comments from the panel?
Yeah, just in terms of trying to find companies to engage with, we've actually found the METS companies to be a bit more open-minded than the mining companies. The METS companies, like Marianne's saying, they're sort of interested in technology and stuff. And the general principle that I keep failing to argue successfully is that if we set the goal, let's do something really hard, like mine water on the moon, and say to a mining company. If the mining company commits to doing that, you'll be able to recruit a whole lot of clever people to try and do it. And on the way, you will solve a whole lot of problems that you've got that you can apply into your terrestrial business right now. But that's not the way they think. It doesn't fit into their existing sort of investment strategy. Actually, I'll give you an example. I was talking to a guy downstairs yesterday about trying to operate robotics in that really dusty environment on the moon. Now, if you were able to come up with a technology that protected your autonomous systems in space from the dust on the moon, you could take that, use it on Earth, and you'd save yourself a whole lot of water in these because the way they keep the dust down in mines in the desert is they put water on it, right? If you save yourself that water, you've solved yourself a problem. So it's just a simple example of how if you apply yourself to the space problem, you can solve a terrestrial problem.
If I may, I have another example of that as well. In mineral processing, what a lot of people don't know about mineral processing in general, it's the separation of minerals after mining. The mining's the easy bit, I like to say. The mineral processing's the really challenging bit. This is my field. Anyway, of course. So of course, it's the hardest. But actually, huge volumes of water are used in mineral processing on Earth. This is what gives us tailings dams that are absolutely enormous. And again, as Andrew said, the example of this is if you are doing any kind of handling, separation of fine, dusty minerals on the moon, then you're not going to use water. Therefore, one can see that there's a direct application of that on Earth as well. And this is something that we do, that I've done a lot in the last few years, and that we do at ESRIC. So there are real clear examples of benefits to both sectors from thinking through these problems in a different environment.
I see. Thank you. Thank you. Well, we've been focusing on lunar application of ground technologies, but the moon is not the only destination for resource utilization. Mark, please share your stories.
Well, my name's Mark Sonter. And I'm the asteroid guy. I'm coming at this with the perspective of about 40 plus years working first as an employee and then as a consultant in the mining industry, providing technical advice in all sorts of different circumstances, large mines, small ones, open pit, underground, different commodities. And about 30 years, that was my paying job, and then about 30 years involvement in attempts to identify ways forward in space mining. I was one of the co-founders of Deep Space Industries, and that happened as a result of me writing a thesis on mining, on the technical and economic feasibility of mining the near-Earth asteroids. So that's my background. I won't go there yet. I'd like to make some comments on this mindset mismatch that's been raised several times by Marianne and by Andrew, and say it's not unique, it's not uniquely difficult, it's not insurmountable to see and overcome these language differences between the space engineering people and the resource project engineering people. These arise from the different mindsets of these different sorts of engineering disciplines. And they're exactly the same as the mismatches that you see inside terrestrial mining projects between the geologists and the mining engineers and the metallurgists. And if you live on a mine site and you work in a mining situation, these sorts of mental mismatches occur all the time. And they're overcome by the chief geologist and the chief mining engineer and the chief process engineer on each mine site having respect for one another and realising that there's this continual language barrier that has to be breached. All of them are joined together by the need to try and make this thing profitable, right? And the other thing that comes out of seeing the terrestrial sector is the extent to which all of these different disciplines are intermeshed and decisions made in one area impact on decisions in another area. The geologist has to try and identify the mineralisation and try and identify within that what's the size and shape of the ore body. They can't do that without talking to the mining engineers because they tell them what the cost of mining is going to be. And they can't do it without talking to the mineral processors because they have to say, well, we can only get 60% recovery or maybe we can get 90% recovery. And that brings in the financial people. So you've got this entire value chain even before exploration starts, from identification of your commodity and what you're trying to chase and where, through to identifying the mineralisation, to identifying the prospect, to then working through this stepwise process similar to the one that Andrew talked about. In Andrew's case, he was talking about the mission design review, the preliminary design review, the critical design review process that the spacecraft engineering people go through in engineering their spacecraft and their space mission. And in the mining situation, we have a studies sequence which goes concept development, scoping study, how big's the project going to be, what's it going to look like, pre-feasibility study, final feasibility study, and then finally the board says, yes, we've got something that the business case will close with and we'll proceed, and then you design, construct, commission and operate. So there's this quite complex and long value chain that we see in the terrestrial mining industry that will have to apply also in space mining, in space resources development, with the added bit that you have to include in the spacecraft and the space engineering, the missions engineering, the trajectory and the propulsion for getting a commodity back to market. So I see all of this as being driven by this long, complex, interrelated and feedback loop dominated value chain, okay? So now onto my own particular pet love, and that is near-Earth asteroids. Now, When I first started studying this seriously, there were about 400 known near-Earth asteroids. There's now about 40,000, and about 20% of them are technically easier to get to than the Moon. Easier to get to than the Moon. There have been deep space missions that our colleagues in Japan have done that have blown away the proof of capability of doing this sort of stuff technically. Marvellous stuff. Good projects that are both highly accessible, good targets, that are both highly accessible, highly prospective, and easily diggable, apparently. So, near-Earth asteroids, humanity's gateway to space. Unlimited self-sustaining human activity in space needs access to in-space resources. There are many, highly accessible and highly prospective. Highly competitive compared with the Moon. There are emerging markets for fuel, particularly in space, that look as though they're going to be $5 to $10 billion per year, 5 to 10 years from now. The project design task is market-driven and parallels terrestrial greenfields mine project planning. Space resource projects are just mines, albeit very, very far away. Okay, they're very remote and very high value, and we must apply terrestrial mine project planning disciplines for crucial guidance. Quick plug for my company, Off Earth Resources. We have a unique background in terrestrial resource industries and in the space industries. We've been developing these sorts of concepts for a couple of years. We have a rigorous space mining project concept that gives a really short, really low capex, risk minimised pathway to commercial access. Actionable now. Thank you, everybody. That's it.
Thank you,
Sorry,
Mark.
I went over.
Yeah, let's move on to Catherine's presentation. What is the overarching goal of your institution, ESLIC, European Space Resources Innovation Centre?
Thanks, Jen. Yeah, we're the European Space Resources Innovation Centre based in Luxembourg. Just to follow on from Jonathan's comment about Australia being a home of abundant natural resources, this is true. But a little known factlet on Luxembourg is actually Luxembourg made its money in iron ore. So it's got a rich history in iron ore mining before the financial sector took over. And then now we return back to our home with space resources. So ESRIC is, for those of you who don't know, it is 5 years old. We're about 30 people. We're our initiative of the Luxembourg Space Agency as part of the spaceresources.lu initiative. And we have a simple and bold mission, and that's to be a world-leading centre of excellence in space resources. But what I want to focus on here in the next 2 minutes or so is startups. So Mark mentioned that Off Earth Resources, I'll get it right eventually, is a startup. And Marianne also mentioned about the opportunities for spin-in, spin-along, spin-back, and so on. What we do that makes us unique in ESRIC, in addition to our research and other activities, is we run a business incubator and a business accelerator. And this is in partnership with the European Space Agency. So with our incubator program, it's open to startups in space resources around the world. But one of the challenges we face in supporting these startups is in the issue of these markets being a long way off. So how can we support startups when the opportunities for near-term revenue are not that clear? And so we spend a lot of time discussing that with our program. How can we support them? What are we looking for? And often what we're looking for is terrestrial applications of technology, because this will allow our startups to thrive, to bring in some revenue as they develop their space resources business. And so it's exactly this. We are looking for those opportunities for terrestrial applications or other applications of their business so that they can grow whilst we are working in this very uncertain sector. So just some words on the Startup Support Programme, if you have a startup or know of a startup in the space resources sector. So, like I say, this programme is open around the world. We run it once or twice a year. We will launch our next call towards the end of this year. We set a call and then we select 5 startups, and they undergo a 12-week remote pre-incubation. You can see on the screen some of our cohorts so far. The ones that are now orange are the ones that we've carried on supporting through incubation in subsequent phases. And it's through these kind of initiatives that we can try and really nurture this emerging sector. One final point, and I will come in under time. And that is, if you would like to know more, come to Luxembourg. Here's my advert for Space Resources Week. We hold it every May. Come to Luxembourg, 4th to 7th of May. It's a beautiful time of year. And you will find a really vibrant, dynamic gathering of the space resources community. This year we were around 470 people. The year before about 450. So it's a really broad and dynamic meeting. So that's my advert. Thank you.
Thanks, Catherine. Thank you. Yeah, let's move on to the second round of discussion. Over the past few decades, the landscape of space exploration has been changing from government-driven to government-led to commercially driven. I think lunar exploration is following the same path in 2020s and 2030s, and of course, the role of each player is changing. So, Marianne, what do you expect may help to promote resource development in space from industrial perspective?
I think the short answer is that for a long time the industry is still going to need government support or support from other bodies because it just isn't commercially viable at this point. Yeah, that's the short answer. Mm-hmm.
Right. And Helen, Andrew, you have been in this field for a long time. And do you feel any changes in the role of academic institution? And do you feel any challenges in collaboration with government body and industry?
Yeah, I think I'd probably comment a little bit more about the government industry thing rather than the academic side. But a statistic that was published quite recently about New South Wales, the host state of this event, the guys downstairs, they set up a space startup hub, just to come, your point reminded me of this, that they found that the state government spends their money on lots of things. In fact, in Australia, it's a federation, so the states spend more money on things than the government does. And the New South Wales government found that the space startup hub that they're operating probably within a half-hour walk of here gave them the best rate of return of anything they spent their money on. Anything. Health, blah, 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 whatever. Now, make of that statistic what you will, but I'm going to say it to everybody I meet, right? So the space resources startups have that on their side, that they can deliver to their government partners big returns on investment. But I'd come back to the point that I made earlier, is that most of the companies, the really successful ones in Australia that have been space startups, like Fleet, like HEO, right? They started out with some goal, which might be space resources, and then they pivoted and they really made a profit out of that pivot. Now, the point I'd make with with this particular application is the point I was trying to make earlier, is that you have the space resources thing as your goal and you make your way there. You make money with the steps along the way. I'll use as an example the company I just mentioned, HEO. They started out wanting to track asteroids and take pictures of asteroids. Along the way, they pivoted to being the first commercial company in the world to take pictures of objects in space from space. Now they're going to go to asteroids. So the way to do it is to find a way to make money along the way, and you can still do it.
All right. Any comments? Yeah.
Andrew, that's exactly what we see a lot with our startups as well. They start with a space resources idea, and then through the pre-incubation phase, certainly we start to see some kind of through coaching and business planning, the need to identify something that can keep them going whilst they work towards the aspirations of space resources industry. So this is exactly what we see also.
Yeah, and the hypothesis I want to test at the moment, right, is I think there's probably about 15 space startups that 10 years ago there weren't many space companies in Australia. I think there were 2. And now there's, whatever, a couple of hundred startups have come along, but about 15 of them have had serious investment. None of them have government as a customer, as prop-up customer. All of them had government help at the beginning. So the role of government in these startups, I think, they help them get on their way, and then Australian startups have to go international early, and all of those successful startups have gone international early.
Yeah, John, and I was just going to say, I work for the government. I'm with Australia's National Science Agency, CSIRO, and so we have a very interesting role to play as well, because we actually exist for the benefit of Australian industry, but we utilise science to do that. And a critical part of that is partnerships. So yes, we do receive government funding, but not completely for the ambitions that we want to do. So to that part, we just say that there are incredible opportunities for partnerships. So although you may not get an explicit, government grant for one particular research aspect that we'd like, there are pathways and there are opportunities, and a critical part of that is actually knowing who your stakeholders are and having those relationships, which is why this forum, I think, is just so important, to make sure that message is being communicated and advocated, so that partnerships are key. And we, as I said, there are other ways we can do it. It is a non-conventional industry in some ways, so perhaps we shouldn't be expecting to be able to completely follow the path of some other industries. It's quite different in lots of ways, but there's a lot of functional similarities in terms of the core technologies and maybe the processes that are involved, that I think there's a lot that we can be doing.
Can you elaborate a little bit more regarding international efforts?
Yeah, and look, we're just talking about Australia, but I'm pleased that you put that up. Jun and myself were involved in a number of other agencies putting together a roadmap that identified what from agencies all around the world, what were the strategic knowledge gaps. So Jun's referring actually to a report here that it's publicly available. It's about 130 pages and appendices. It's probably the best condensed resource that I've ever seen in terms of what the key strategic knowledge gaps are all about. In fact, I'm doing a paper tomorrow to make sure people know about it and how we've been using it. It's page 28. If you've got no time, go to page 28. There's a beautiful functional flow diagram that shows the kinds of systems and architectures that we need to be looking at. And what's important in that report, agencies from across the world have indicated what they felt their capabilities were, what the sequence of activities should be, right from raw materials to the products, and finally the applications, which is coming back to that commercial aspect, or at least the service or the value aspect. Not everything is completely driven by commercial things. For other people, particularly scientists, technologists, there is also a value in the science and the insights that then yields, but then often bursts into other applications for industry as well. So, thanks.
All right, we have some time for questions. Please show the QR code. Technical team, please. Please post your questions on Slide Up so that we can pick out some. Well, any questions from the panel? Oh, no questions yet. Oh yeah, that's great.
Sorry. Thank you so much. I am Surya Pratap Singh, a PhD student in Swinburne University. And since since 4 years, I am working on ISRU. In simple terms, my PhD thesis was titled on lunar steelmaking. And I went to many conferences, and it was like no one was understanding why I am doing it. So I'm so happy to see you, all the people who started the ISRU thing. And like from the Colorado School of Mines, we are just following your thesis, chapters, papers, and everything. So my question is, how do you think, like we kind of sometimes we get demotivated, like what will happen after this research? Because we don't see any company directly recruiting for ISRU or something. So what do you see, like where can we see the ISRU reality happening, like in my next 5 years or 10 years? when these technologies will become like officially now we can work on this?
Yeah, no, that's a common feeling with students that are involved in this field. When we started, we were a little bit afraid there was not going to be any opportunities, but you start seeing now more and more. Obviously, space agencies, you got now all the major launch providers have some sort of department or division on space resources. You start seeing not just space agencies, but the departments of, in the United States, the Department of Commerce, the Department of Energy, even the Department of Defense. You start seeing there's more than 150 companies that are startups that are looking into this. Some of them are successful, some are not. But we start seeing the opportunity now because things are slowly moving. I mean, those successful companies that are applying it for terrestrial mining, now they're offering, just this year, you've seen companies that put a drill on the moon. You're going to see demonstrations of extraction. And when that starts happening, then you start seeing more and more opportunities. And I think that the future is bright. You just have to be patient. It's a slowly developing field. But once it takes off, I think it will make quite a difference.
Yeah, cool. Can I just add something? So we love Swinburne. Well done. We love ISRU. We've got people from Swinburne working at CSIRO, which is really good. To your point, if you like Star Trek, there's a scene there where Spock realises he's a child of two worlds, both Earth and Vulcan. I think to a certain extent we need people who can be, children of two worlds. I mean that seriously. There's a development that you need to keep doing. Don't lose the fire for Earth planetary resources. But practically speaking, we're looking at decarbonising the whole energy market. And if you can figure out a way to process steel in environmentally friendly, like green steel, for example, or if you could process that in such a way that it was carbonless, waterless, and low energy, which is what you'd have to do on the moon, for example, to produce metals there, then that would be of great interest, I can tell you, to terrestrial. So I think we have to have a broader lens for a while, and there'll be plenty of gaps once that begins to scale up. So thank you for your question.
Marianne, do you have any comments?
No, nothing to add, sorry.
I'll do your bit. Here's my advice. I would look at the companies that are doing METs, right? You know what the problems on the moon are, right? So if you go to a well-established, innovative METs company that's working on terrestrial problems, but in your mind you've got the space application, then you do a startup, you're a millionaire.
I will just add something there. There's a lot of networking opportunities that I think would help just to really understand how the mining ecosystem works and how you can move from there. I think, and we have a lot of people who from both sectors who attend those sort of networking events, as other networking events as well.
All right, there are a lot of great questions. And here's a question regarding asteroid mining. And what is the first material that could be mined, that can bring back to Earth from asteroids? We have 30 seconds for question time. So
Thank you, Jun. The low-hanging fruit is water, my friend, water, right? And shortly after that, ordinary base metals, nickel iron metal. I warn strongly against thinking about rare earths or against platinum group metals as being early stage or maybe ever major products from asteroid mining. In a very, very mature mining industry, maybe, but clearly water.
right, thank you.
And I think correct me if I'm wrong, but I think you're saying that because we're talking about in-situ resource utilisation. In other words, using the stuff in space. When people talk about platinum, they talk about other things, they're talking about bringing it back. No one's really built a business case for anything yet except possibly helium-3.
Thank you for the clarification, Andrew. I missed it.
All right, we have almost reached the end of our time. And my final question is, what's next for you? And before getting into that, Jonathan, what is the main best good takeaway from today's conversation?
Oh, there are challenges and there are opportunities. If I just listening to what's been said here and what we've spoken of in the past, it's I'm loving the ongoing evolution of the narrative around space resources. It's moving from, I think, go back a few years ago, it might have been somewhat superficial similarities to now we're seeing functional similarities, and you can build on that as a foundation, which is much more interesting. And as we said here, we're pressing into that next tier, the tier below, of detail on what that actually means. So that's a really pleasing thing, and we applaud you all for coming this afternoon to this session to hear more of that. We need you to advocate for clarity on those things as well. Partnership's critical, just critical, and identifying those specific payloads that can be contributing in ways that we can then get them to these exciting remote locations, the Moon, Mars, and even asteroids. So, but yeah, it's a great conversation.
Thanks, Jonathan. Well, Marian, what's next for you?
The future's very exciting from where we sit, and I guess our role and what we're looking forward to is continuing to facilitate the discussions between mining, METS and space, and to, the better we understand each other, the faster we can move and benefit both sectors. And how?
Well, that's quite a question. For me, from now until I depart this planet Earth, which I hope there's going to be many more years, I see that I will stay involved on spreading the message, on educating young and old people on the value of space resources, how resources will not only enable further space exploration, but also will benefit humankind here and in space. So I see a lot of value in that. And if you allow me, keeping on the theme of rock and roll, if I can quote one of the best rock and roll bands in history, the Beatles, and specifically George Harrison, when he said, "Here comes the sun." So from the point of view of space resources, and for all of you here, make note that here comes the sun, here comes the moon, the asteroids, Mars, and beyond. And I say, all right.
Andrew.
Now I'm going to sing a song.
Please.
No, look, I think what's next for this industry, if I was going to say what's the most important thing to do next, I would actually say get the legal side of things sorted out, because no mining company is going to dig something up if they don't even know if they own it when they've done it. And that needs to be clarified. And the UN is moving very slowly on this. The Artemis Accords may not have jurisdiction, so there's all sorts of problems related with the legal side, and some of those, what they call modifying factors in that diagram I had earlier. I think the technical side, people like you are going to solve that. We need more work in the other things at the moment before we can be confident of being able to go forward with this. What's next for us? Well, we've just got for those of you who are coming on the tour to see it tomorrow, we've got a new facility for testing all this stuff, so we're going to be doing a lot more work with the actual regolith. Note that when Angel is holding this up, it does have the word Australian on it. So we've one of the PhD students did a startup making regolith, and he's made a couple of sales, and we're using that in our lab. So there's a fair bit of interesting work to be done. I'll still be working at the high level, not getting my hands dirty with that stuff, but just writing about airy-fairy theoretical things. And then I can retire.
Great plan. Mark?
I'm going to reprise Arnhill. Being an old Moody Blues fan, I'm going to say, see you on the dark side of the moon, Arnhill. However, Pink Floyd, sorry.
Yeah, so there's no dark side of the moon.
That sets what's next for us. I've been trying to zero in on financially supportable, closing business case approaches to mining commodities from asteroids seriously for a dozen years or so, and we're getting very, very close. And the technologies are being developed, and things are being demonstrated. I have this sense that it's really, really, really close, and I just like to leave with everybody with the thought that that asteroid mining and attempts at lunar mining will be happening within 5 to 10 years. And I would like to be there, and I'm at the stage now where we are actively seeking seed funding to proceed with our own project ideas.
Catherine.
Oh, I haven't got long left. Very quickly. What's next for ESRIC? We continue to grow. We're 5 years old, so we're still relatively young in research and innovation centre terms. So we continue to grow. We were super excited yesterday to read the press release from Blue Origin about the Oasis One project in partnership with Luxembourg. And we're looking forward to growing activity there. So we continue to develop all of our activities. But if you would like to find out more, come and join us in Luxembourg next year, and then you can find out all about what we do.
Thank you, Catherine. Yeah, go ahead.
And Jun, just what's next for me, at 3 p.m, which is in 15 minutes, I've got a short 10-minute presentation that's highlighting some 3 or 4 examples of where we've taken literally mining technology and put it into space. So if you're interested in that topic, you can get another 10 minutes if you wish. That's what's next for me, literally. Thanks.
All right.
And let me add one thing. It's just exciting to be in Australia with all this activity that is happening on this Congress, and to see how the country is moving rapidly towards more ambitious plans in space. So I expect that in a few more years, Australia we will be going from down under to up above.
All right. Well, let's keep our discussions from multidimensional aspects to lay the foundation of space resource utilization. Thank you, everybody. Appreciate that.